The next function we are interested in is the search function. We want to search for a number in the list. And so let's start with searching for the number 10. How will I do the search? I'm going to, if I want to search for a number, I'm going to head and I'm going to first go to the node at the front of the list, and I'm going to check whether, so initially I'm going to check for 10, right? I'm going to search for 10. So I go to the front node and see whether that node is 10, and I find that okay, that node contains the element 10, and I'm going to say yes, 10 is there in this list. Next I'm going to check whether the number 5 is there. And how will I do that? I go to the first node of the list and I see that okay, that's not 5. Then I go to the next node in the list, and I go to the next node by traversing through the next pointer in the first node, right? And go to the next node and check whether the second node is 5, and I find that okay, it is 5, and then I will return yes. So let's assume it's 15. I'm going to check for next, and 15, let's say, is there somewhere inside this list. In that case, I'm assuming that 15 is somewhere in this list. In that case, we use the same function, right? So the function goes to the first node, it sees that it's not 15, it goes to the next node through the next pointer. Then it goes to the third node through the next pointer of the second node, goes to the fourth through the next point of the third node, and so on and so forth until it hits 15. And as it hits 15, it's going to return, right, I found out there is a 15, there is a node with 15, and it's going to say yes. Finally, we are going to look at 35. Searching for 35 also goes along the same lines. We go to the 10, we traverse the next to the next pointer to the next node, next pointer to the next node, and so on and forth until we hit on 35. And when we hit 35, we say yes. Now I'm going to check for the number 50 and assume that 50 is not there in this list. If 50 is not there in this list, what will happen? If 50 is not there in this list, we are going to, so let's go through the algorithm. We go to the first node, no, it's not 50. We go to the next node through the next pointer, not 50. Third node through the next point of the second node, and so on and so forth until I reach the last node. And I see that okay, it's 35 and it's not 50. Then how do I know it's the last node? I know it's the last node because the next pointer is now equal to null. Okay, so once I hit the null pointer, I realize that okay, there's nowhere else to go and I am in the last node, right? So that's the crucial thing. How do I detect that I'm in the last node? So that's using the null pointer, and once I am in the last pointer in the last node and I have realized that I have not seen 50 till now, I'm going to say no, 50 is not there in this list. Is it clear? Okay, next question we always ask is how many nodes did we see when I do a search? Okay, now the answer is obviously it's going to depend on the number we are searching for. The question has to have more input. So let me ask you the following question. In the best case scenario, how many nodes do you have to search? How many nodes do you have to see before you return an answer? Okay, the answer can be yes or no, but how many nodes did you see in the best case? Okay, and the answer is 1. Let me note down that in the best case you only have to see one node, that is a front node, because let's assume you're searching for the number 10 and you go to the first node and you realize that yes, that is 10 and you're going to return 1. So that's good. Now what about the worst case? So always assume there are n elements in the list. So if there are n elements in the list, how many nodes will you see in the worst case? N, right? What is the case we are talking about? The case is there are two cases actually. One case is we are looking for the number 35, that is the last number, a number which is in the last node. In that case, we'll have to go through all the elements of the list before I hit on 35, and therefore in the worst case I have to look at n nodes. There's a second case of I'm searching for let's say for the number 50, which is not in the list. Even in that case, I reach the last node and then I decide no, I haven't seen 50, and so therefore I'm going to say no. Even in this case also, I traverse n nodes, so this is also another worst case scenario. The next function The next function I'm interested in is the length function. So someone is asking you what is the length of the list or how many elements are there in this list. What is one way to answer this question? One way to answer this question is you traverse through the entire list. Just like you're searching for the elements, you traverse through the entire list by keeping a counter and you keep on counting, right? You keep on counting and you realize that you stop when you reach the node with the null pointer. So then the counter is basically giving you the count and you can return that count. That's the length of the list. Now you should tell me how much time does it take. So again, we are going to assume n elements. So if there are n elements in this list, how much time does it take to find out the length, right? So time in this case is I'm asking you how many nodes did we visit to find out this. The answer is n. I visited n all the n nodes to I had to go through all the n nodes to answer the length is n. So again, to find out the length, it's going to depend on the number of elements. The time, the number of nodes it visits is going to take or depend on the number of elements. So if the list had 1 million elements, it's going to take that much time compared to if the list had only, let's say, 10 elements. Right now, again, it's up to a implementer of this ADT whether you need to spend this much time or not to find the length. Maybe it makes sense to return this answer quickly. Is there some way, as the maker of this linked list, you can do something so that you can answer this question very fast? As soon as someone asks you the length, you can return the answer. Can you modify this? Can you modify your linked list structure or your linked list class to ensure that you can answer, make it much faster than this current method? So here is an answer. What I'm going to do is the following. I'm going to keep a counter as part of this class, and every time I add an element to the list, I'm going to increment the counter, and every time I remove an element, I'm going to decrement the counter. In that case, as soon as someone asks me what is the length of this list, I'm going to return the counter value. Is it clear? So whenever I add an element, I increment the counter. Whenever I remove an element, I decrement the counter. So this maintains the length, right? This maintains how many elements are there in this list. And so when someone asks you this question, what is the length of the list, you just have to return the counter value. This is one way you can make the length function much faster. Now in this case, you can see that the number of node visits in this new case is 0. So this is much faster. So this is modified version. So in our modified version, the number of node visits is 0. The next question we are interested in is add an element to the back of the list. Okay, this is a little tricky. How do I add an element to the end of the list, right? So let's assume I want to add the element 100. What I want is I want the 100. Okay, I can create a node with 100 value, and since it's going to be the last node, I will make its next to be equal to null. But I want to ensure that the last node in the current list is going to point to 100, the node 100, right? How will I do that? So to do that, we need to first get to the last node, because only the last node has the next value, and I have to change the next value of that last node to this address, right? This is what we need to do. But the problem is I don't know where is this last node sitting, right? I don't know where is this last node sitting. Its address is available only in the previous node, right? And then, so that means I have to know the second last node. I need to access the second last node in that case. Now, if I have to access the second last node, the address to the second last node is only in the third last, right? So similarly, I can keep on arguing and I can reach the front node. I can say, okay, where is this front node sitting and what is the address of this front node? And that address is in the head node that we know, and therefore we have to traverse this entire list to find out this last node in the current list. To get the last node in the current list, I have to traverse this entire list, and I have to take its next value and change that value to the address of this newly created node, which has its value 100. So as you could see, now the question is how much time does it take, right? So how many nodes does this, we are going to say there are n elements. If there are n elements, how much time, how many nodes do we have to visit to add a new element in the back? And again, you can see that we have to visit n, or you can say even n plus 1, because we have to create this new node also. So we had to visit n plus 1 nodes to add a node to the back. So can we do something about it? That's the question. Can we modify it? So if, let's say, we want to provide a data structure which also gives the user flexibility to add an element to the back of the list. The user is interested in adding an element to the back of the list also in by looking at only one node, just like he or she can add a node at the front of the list. We need to give that flexibility. So we are going to modify this list so that that's also possible.